Today I'm going to talk about a few highlights only from the many new results that were delivered by CoRoT and Kepler. So I'm going to focus on RR Lyrae stars that are horizontal branch large amplitude pulsators, and they are well known being excellent tracers of the galactic structure and very good distance indicators. Last but not least, they are very good test bed objects for studying various nonlinear dynamical phenomena related to the pulsation, stellar pulsation. These are my colleagues in this collaboration. This is basically the CoRoT RR Lyrae working group, and some of the results will be based on the KASC, Kepler data. So I would like to thank all these people for their hard work and dedication. Before we start, I would like to start with a story. Back many years ago, a colleague came to me and asked, what are you going to do with those space-based RR Lyrae data? These stars are so boring. And I said something like, well, we haven't seen the space-based data yet, so those will be excellent, very precise data. And indeed, during this space photometry revolution, many new things were discovered and published connected to RR Lyrae stars, from high-order resonances and high-order overtones, additional frequencies, and period doubling, even chaos, irregular modulations, and even a new explanation for the mysterious century-old Blazhko effect, Blazhko problem. So today, I could answer differently, and of course, these are not boring stars. They are really interesting, and I hope that by the end of my talk, you will be all convinced that these are very interesting objects. So one of the most important discovery, in my opinion, is the discovery by Kepler of the period doubling, which is a well-known dynamical effect. You see these alternating maxima right here throughout the Kepler observations. This is Q5 Kepler data, short cadence, so thank you very much for insisting keeping these options, the short cadence, which is very important. So that's what you see in the light curve. In the frequency domain, you have the half integer frequencies between the fundamental mode frequency and the harmonics. So in between, halfway, you see these frequencies that indicate that there's a period doubling going on in this star. So period doubling bifurcations are very important for many reasons. One is that this is the way to go from regular observations, regular pulsations, to chaos. So that's what you see in our models here, where real dynamical thing, period doubling bifurcations are happening right here. So the other important thing is that period doubling and the Blazhko modulation is these are intimately connected. So we see period doubling only in Blazhko modulated stars, and none of the non-modulated stars show period doubling, even to the precision of Kepler and CoRoT. So this is a very strict relationship. And the third thing is that we were able to show that the period doubling is caused by a 9-to-2 resonance, a high-order resonance between the fundamental mode and the 9th radial overtone. And even it is possible to show mathematically that this very same resonance that causes the period doubling is able to create the Blazhko mechanism, the modulation itself. So it's a very important relation, and because of that, it's important to check the statistics. And recently we found that by Kepler, that out of 16 Blazhko modulated stars, 10 of those show period doubling. And recently we were able to add 4 new candidates from CoRoT, and that's what I'm going to show you. This is the family portrait of the CoRoT Blazhko stars. These are all light curves folded by the Blazhko period, and we have 6 of those, and these 2 are heavily blended, actually. So you'll see the large scatter. And we found the period doubling very clearly in 4 of these stars. This is V11, 27 Aquilae. You see the half integer frequencies in the frequency domain. You see the alternating light maxima in the light curve. We have other objects as well. Here you see one of the heavily blended one. You see that the total amplitude is around 200ths of a magnitude. So it's really a heavily blended star, and we still see the alternating maxima. So it's very important. So to conclude this part of my talk, Kepler and CoRoT enabled us to derive these statistics that 2 out of 3 Blazhko modulated stars do show the period doubling. This is very important. The next part, I'm going to talk about additional modes. So we have these half-integer frequencies in the Blazhko modulated stars, and here I show 16 Kepler Blazhko stars, and the frequency spectrum between the fundamental mode and the first harmonic. So this is a very important part of the frequency spectrum, and the middle yellow band shows the half-integer frequencies. You can see those here. And the other 2 yellow bands show the theoretical prediction of the location of the first overtone and the second overtone, radial overtones. So what you see here is many of these stars show power around the second overtone, and also some of those around the first overtone. So we have 2 options here. We have either the radial modes are excited, and indeed in one case, at least in one case, in RR Lyrae itself, the prototype, we were able to show, to demonstrate by models that the first overtone, the radial one, is excited. Or we have non-radial modes coupled to these radial modes as predicted by earlier theoretical work. So we might have non-radial modes here. And I switched to the CoRoT sample, and we see the same pattern here. These are the 4 stars showing the period doubling. And what is really exciting and striking is that if I add the non-Blazhko stars, the frequency spectrum of those is completely different. They have no additional modes, no additional frequencies or modes right here. These are normal constant amplitude non-modulated RRAB stars. So there's a huge difference between modulated stars and non-modulated stars. And beyond the radial modes, there are modes left here which are cannot be compatible with the radial eigenspectrum. So these should be non-radial modes. I show here some examples, CoRoT examples for RRAB stars and one example for RSTC stars. And one particularly exciting period ratio is around 0.61. And this is obviously not a radial overtone. And it is also seen in Cepheids, overtone Cepheids. And we also have in all RRC, first overtone pulsators, and RRD, regular canonical double mode pulsators. So we added new stars from the CoRoT sampler here. And actually, all of the RRC stars and RRD stars that we know, that have been observed with space-based data or spacecraft, are showing this period ratio. So to wrap up, it's very important to summarize these findings, that actually all of the Blazhko modulated stars and all the RRC first overtone stars and the canonical fundamental double mode stars do show these additional frequencies. And a very important exception is non-modulated stars. We do not see additional modes here. We went a step further and checked the temporal variability of these additional modes. And you see one example here. This is the half-integer frequency. This is related to the second overtone. This is one example. We have several examples. This is the conspicuous 0.61 period ratio frequency. And you see a temporal variation, not only in the amplitude, but also in the structure of these modes. So there are 2 possibilities. One is, both of them are very exciting from the theoretical point of view. First, if we have a real amplitude variation here, then these modes should have to be coupled to the radial modes and the non-radial ones, so there might be a very interesting interplay between those. And if there are unresolved modes here, and that's why we see this structural variation, then again we have a lot of other modes that we have to find an answer. What is the cause of those, of the presence of those additional modes? One thing we can do is these are CoRoT examples. We can go to the Kepler sample and we can check. We have longer data, and that's a work in progress. We can check whether we see additional modes very close to these additional ones. That's another example. And in conclusion, I could say that this temporal variability is again ubiquitous. So it is in all stars that feature these additional modes. It's very interesting. It's not only one or two objects, actually all of the objects that we checked show this temporal variability. My last point is about the modulations, the Blazhko modulations. You see this very nice modulated Blazhko light curves. These are these 16 Blazhko stars in the Kepler sample. And the question is whether this Blazhko modulation is nice, simple, sinusoidal, or not. And the answer is not, none of these. You see that they can be very, very complicated right here. Actually, we just published this paper, and we make available these final, rectified, normalized, staged, final 4-year-long Kepler Blazhko light curves. So if you want to have a textbook example, you can just go to this website or the FJ supplement website and download those. So actually, there were indications that in some individual objects, there might be more than one modulation periods. And in a recent survey based on ground-based large sample, it was found that 12% of those stars show multi-periodic or irregular modulated modulations, light variations. But with a Kepler sample, we have a much, much higher number. It's more than 80% of those stars show multiple irregular variations. I show the same thing. This is the O-C diagram of some of those Kepler light curves. You see that the Blazhko modulation comes with a frequency modulation as well. And this plot shows the low frequency part of the frequency spectrum of the light curves of these stars and the O-C diagrams. And what is interesting that besides the Blazhko frequency and harmonics, and besides the Kepler instrumental signals, the Kepler year and its harmonics, you see secondary modulations all around in many of those stars. These are these blue circles right here. So to wrap up, the multiple modulation in the Blazhko stars is the rule, and it's not an exception. And my last slide is on a sneak peek into the future missions. K2, TESS, and Plato will be very important because they will deliver, they will survey different populations. They will cover the whole parameter space. They will deliver and observe rare objects, and will give us much, much better statistics, thousands of stars. So far, only a few dozens were observed with Kepler and CoRoT. And here are a few preliminary results from the K2 engineering data. These are very nice objects already, rare gems. We have a canonical RRD star here, a double mode one, a very nice amplitude modulated RRC stars. We haven't seen that yet in the nominal Kepler mission, nor in CoRoT. And we have a Blazhko star with period doubling, signs of period doubling right here. So these are my conclusions. RR Lyrae stars are interesting. Period doubling is seen in the majority of the Blazhko stars now. Initially, a few years ago, we found it in some stars, but now in the majority of these stars show period doubling. And even if we consider that period doubling is usually seen only in short sections of the light curves, then these 2/3 or 66% can be even higher. The additional modes are everywhere in these stars, except the non-modulated stars, RRAB stars. That's where we can start to scratch our heads. Why is that? And the cause of the additional frequency, temporal variation, is not really well known, not really understood yet. And multiple Blazhko modulations are very common, and we are facing a very bright future because of these upcoming future missions. And one last note, we are going to have a Kepler splinter session on RR Lyrae stars and the Cepheids in the splinter meeting in this lunch break today from 1:30. So if you are interested, interested, you are very welcome. Thank you very much for your attention.